Did you calculate the speed? It comes out to be about 1418 RPM and not 1500 RPM as we wanted it. Remember, to have the motor run at 1500 RPM required an armature voltage of 230 volts, and that was coming as the output of this box Ka, for which therefore the input required was 1.15 volts because Ka was 200, which means that the error signal E is to be 1.15 volts, whereas the reference voltage was 20. Because of that, the tacho generator voltage would have had to be 18.85 volts, that is 18.85 volts, which means that the motor will not be running at 1500 RPM. In fact, 18.85 volts will be produced by the tacho generator at a speed of about 1413 RPM. So this qualitative argument goes to show that the speed of the motor could not be 1500 RPM. But then by making actual calculations with the three equations that we wrote down, you will find out that the speed comes out to be about 1418 RPM. So that the error voltage is about 1.09 volts and the tacho generator output voltage is 18.91 volt rather than 18.85 volts. Now the point of the whole argument was that if we have a feedback control arrangement like this, which is said to be the proportional control type, in which the error signal is the difference between the reference signal and the feedback signal, and the reference signal represents the desired quantity, and the feedback signal, in this case the tacho generator voltage, is proportional to the output quantity. So if we use proportional control scheme in which the error voltage E produces an output, in this case our armature voltage, which is proportional to the error voltage. Remember, the type of the system was 0, in the sense constant armature voltage would produce constant motor speed current. So if the motor speed is the output and armature voltage is the input, then the DC motor behaves like a type 0 system. So we have a type 0 system with proportional control, and if you look at most of the textbooks, you can look at the formula for the steady state error, and it will turn out that there will be a steady state error. And this is what we actually found out, that instead of 1500 RPM, the speed will be 1418 RPM. Now of course one can say that the amplifier gain Ka was only 200, you required an error voltage of 1.15 volts to produce an output voltage of 230 volts, which is going to the armature. So let's increase the gain of the amplifier so that the error voltage required to produce 230 volts is much less. Alright, let's increase the gain by a factor of 10. So make now Ka equal to 2000 instead of 200. The error voltage required to produce 230 volts therefore will not be now 1.15 volts, but will be 1/10 of that, that is 0.115 volts. The reference voltage is 20. So the tacho generator voltage will still be less than 20 volts. It will be less than 20 volts by this smaller amount, 0.115. So it will be about 19.885 volts, but it will not be 20 volts, and so the motor speed once again cannot be 1500, but will be something less than 1500. And you can redo the calculations with the gain Ka equal to 2000, and you will find that the speed will be now much closer to 1500 RPM than the earlier answer of 1418 RPM. But still it cannot be exactly 1500 RPM, and this is why the books say that there will be a steady state error which is non-zero. If you increase the gain still further by another factor of 10, then the speed will be still closer to the desired speed. But the point is since you have an actual amplifier, some error voltage is required to produce the output voltage of 230 volts, and therefore there will always be a steady state error, that is, the motor will not run at the desired speed. Now in a way this is absurd, because this means that you cannot design a drive so that it will run at a desired speed using this idea of proportional control, at least. So there should be some way of getting over this situation, still keeping the idea of proportional control. And indeed it is possible, and you will also see where the mistake we are making is, or what is the error about error that we are committing. We want the motor to run at 1500 rpm, so let us say that we still use the same tacho generator, so its output voltage will be 20 volts. If the motor is to run at 1500 rpm, the tacho generator is unchanged, the tacho generator output voltage will be 20 volts. There is nothing we can do about it now. Similarly, the armature voltage required is 230 volts, and therefore if we keep the same amplifier gain Ka, the voltage E, the so called error voltage, or the output of the difference device, will still have to be 1.15 volts. But now, instead of keeping the reference voltage at 20, why don't we increase it so that that voltage minus the tacho generator voltage 20 is equal to 1.15 volts. And so all we have to do is we have to change the reference voltage from 20 to 20 plus 1.15 volts, or 21.15 volts. Now you can redo the calculations with a reference voltage of 21.15, Ka equal to 200 as before, everything else as before, and you will find out that the output speed will come out to be 1500 rpm as is desired. So the reference voltage, instead of 20 volts, which corresponds to the tacho generator output voltage of 20 volts at 1500 rpm, is to be a little more. And how much more? Exactly the amount that is required to produce the desired armature voltage, in this case 1.15. Now this is why I mentioned that perhaps it is not correct to use the word error for this output of the difference device, because the motor will be running at 1500 rpm, tacho generator will produce 20 volts, reference voltage is 21.15, the output of this difference device is 1.15 volts, which produces 230 volts, which therefore ensures that the motor runs at 1500 rpm. So the drive has no steady state error, the drive is running at 1500 rpm. So this E, which is 1.5 volts, is not really the error, in the sense it is the difference between the desired speed and the actual speed. It is the output of this device, the difference device, or the error detector or comparator, which is taking as two inputs a reference voltage, which is to represent the desired value, and the feedback signal, in this case the tacho generator voltage, which represents the actual value. So this E should not really then be called the error, in the sense it is not related to the error in speed. Now this is one way of rectifying the situation. All that I have done is I have kept everything else the same, tacho generator unchanged, gain Ka unchanged. I have simply changed the reference voltage so that it is not 20 volts, but it is 21.15 volts. And why didn't I think of it earlier? Because the thinking was that the desired voltage should be 20 volts, because the tacho generator output voltage at the desired value is 20 volts. And so let's have reference voltage equal to 20 volts. Now what we are doing is, the desired speed 1500 rpm is not represented by 20 volts, but is represented by 21.15 volts. Now that's okay. The desired speed is to be represented by some voltage, and in this case that voltage is such that with a specified feedback arrangement, namely the tacho generator, and a specified proportional control arrangement, namely the gain of 200, the reference voltage which represents the desired speed is just the correct value, not 20 volts but 21.15 volts, so that the drive runs at the correct speed. This is one way out of the situation. So we have changed the reference voltage and we have changed our way of thinking. All that we are thinking now is the reference voltage represents the desired value. The tacho generator output gives you the actual value. The only thing is, these two need not be the same when the drive runs at the desired speed. We sort of use one representation for the desired value and we get one representation of the actual value, so that there is a non-zero difference between the two when the conditions are the desired ones, which produces a non-zero voltage which causes the motor to run at the correct speed. What is the second alternative? Suppose I want to keep the reference voltage the same, 20 volts. Say I have bought my 20 volts supply or whatever it is. Now, and I don't want to touch the amplifier gain will be still 200. Then what has to change now? 20 reference voltage unchanged, the output required is 1.15 volts, that's unchanged. So what do I require now? I require a tacho generator voltage which is no longer 20 volts but 18.85 volts. Now if my tacho generator is producing an output of 20 volts at 1500 rpm, I have two alternatives. Either I can replace the tacho generator by another which will produce 18.85 volts at 1500 rpm, or alternately I will use the same tacho generator but take only a part of its voltage, for example through a resistance divider network or a potentiometer arrangement, so that from the 20 volts produced by the tacho generator only 18.85 is taken and given to the error detector. With this also then the motor will run at the correct speed, 1500 rpm, tacho generator output will be 20 volts, but not all of it will be fed back. 18.85 will be fed back to the error detector, for which the other input is the reference voltage which we have kept at 20. So there is a difference of 1.15 and that produces the correct value 230 volts and therefore 1500 rpm. Now in this second case, one sometimes talk about non-unity feedback, and in fact these are the two terms which are used in the literature, and they can also give rise to this confusion, or they are another way in which the same confusion can arise. So one distinguishes sometimes between unity feedback system and non-unity feedback system. Now what is the difference and what are these two? In fact, in most cases these two terms cannot be applied directly to the actual control system configuration. They can be applied to a block diagram that we can draw, and then we can say, all right, this signal here should be nearly equal to that signal there, or this signal here is 0.8 times that signal there, and things like that. So on the block diagram we can certainly indicate signals and say that under ideal conditions these two signals should be equal, or one of the signals should be equal to 0.8 times the other or 0.9 times the other, and so on. And there is a good reason for this. Let us get back to our speed control system. What was the output quantity? 1500 rpm, the desired speed. Now we didn't want a shaft to run at 1500 rpm so that we can check whether the actual motor shaft speed is 1500 rpm or not. That is, we did not want to compare the shaft speed of the motor under actual operation with some other shaft running at that constant speed of 1500 rpm, because it's inconvenient. I need a synchronous motor, the supply voltage will have to be at 50 hertz frequency, and then what do? I have two shafts running at two different speeds. How do I even find out whether they are running at the same speed or not? and then take some action based on that. So this is thoroughly impractical. As a result, therefore, since we are already using a generator and a motor and whatnot, we decided to use a tacho generator to represent the desired quantity, and also the actual, not represent the desired quantity, actually to represent the actual quantity. The 1500 RPM or whatever RPM the motor runs at is represented by the tacho generator output voltage. So the feedback device, if it is the tacho generator, its output is voltage, its input is RPM. Its output is 20 volts, its input is 1500 RPM. Certainly voltage is not the same thing as RPM, nor is 20 volts or 20 the same thing as 1500. So am I using unity feedback or non-unity feedback? In fact, that question does not make sense in this context. The input to the whole thing, because the feedback signal was a voltage, because it is a field current which is to be adjusted or manipulated, because the field current will be manipulated by changing some voltage, because the voltage can be produced by an electronic amplifier. Therefore, we chose the reference input also as a voltage. We did not choose the reference signal as a 1500 RPM shaft, but it was a voltage. Similarly, the error signal or the difference or the output of the error detector or comparator is also a voltage. So they are all voltages there. RPM we have left behind, although the interest finally is in the speed. At the input end, we are really working with voltages only, and this is what is likely to happen in most control applications. The output variable will be speed, angular position, so it will be degrees or radians or whatever way you want to specify angle, or it could be pressure, it could be temperature, it could be velocity of some particle, or it could be the rate of flow of some fluid, or it could be the concentration of some chemical in a mixture, or what have you. It will be a physical quantity of some appropriate kind based on the application. The input quantity, on the other hand, is not going to be any one of those things. In most of the cases, the input quantity will be a voltage. Of course, the input quantity may not be a voltage as such on the face of it. Think of the air conditioner for a moment. How do you adjust the temperature? You don't directly fiddle with any voltage as such. What you do is there is a knob on the air conditioner panel and you turn the knob. So in this case, the input is the angular position of the knob, or to change the input we have to turn the knob. And this is very often, when there is a manual element involved, this is very often how we control anything. You control the air conditioner temperature by changing that knob, or if you have a remote control for it, then you will press a button somewhere and then see a number come up which will say the temperature that you want. Or if you are driving a scooter or a car, it's the steering wheel and the accelerator pedal and the brake pedal or the grip bar for the brakes. That is what you are going to control. What you are going to control, of course, is the speed of the vehicle, the position of the vehicle, whether the vehicle is going to turn or go straight, and things like that. So the input variables or the reference variables are quite different in physical nature from the output variables, and so their values are also quite different. So it's extremely rare that the reference signal will be of the same type physically as the output that is being controlled. So this is volts, that is volts perhaps, or this is degrees, that is degrees, of the same type. Not only that, they may be of the same level, of the same range of values. The reference input is of the order of some volts, say 10 volts, then the output voltage is also of the order of 10 volts. It is only rarely that this happens. And just about the only case in which this happens is precisely the case of another kind of system that I mentioned in the beginning. What we are talking about, motor speed control, is a regulator type system. The goal is to keep the output quantity constant. In contrast with that is the class of systems called the servo mechanisms or follow-up systems or tracking systems, in which the system produces an output quantity which is to track the input quantity. And in the case of our radar gun control system, the output is angular position of the gun, and the input would be, if the input is not being tracked by means of a radar, but let us say the gunner who is sitting on the tank on which the gun is located, or if it is not on a tank, it is stationary wherever it is, he has a line of sight, that is, he has a telescope which he turns, and once the enemy aircraft is in his field of vision, then he tries to follow it or track it. So he moves his telescope. So there is the movement of the telescope as the enemy target is moving, and you would like the gun to move correspondingly. This is about the only kind of situation where you have an angular position, the angular position of your line of sight or telescope, and then you have the angular position of the gun, the system being controlled, and the two have to be equal. They are equal, not only they are equal in the physical sense, that is, both are angles, and both should be equal in the sense, if the telescope is pointing at, say, 40 degrees elevation and a certain azimuth angle, then the gun ideally should also be pointed at almost the same elevation and the same azimuth angle. So in this sense only, the input value will be comparable to the output value, both will be of the same kind, and I can talk about a direct comparison between the input angular position, the position of the telescope sight, and the output angular position, the position of the gun. These may be measured, of course, not directly. The gun may be out there, the telescopic sight may be at another place. So you are not going to couple them mechanically and compare the two positions. Each angular position will be represented. Now this is a key idea, that is, what we want to happen is that this angle signal should be equal to this angle signal as far as possible, it should follow. But what we measure, what we do is that we convert them, if you wish, transduce them or sense them, and instead of angles we work with voltages or amperes, currents, or whatever convenient quantity, so that both these angles are going to be represented by some other physical quantity, perhaps voltages. And in fact this is what is actually done. I mentioned a device called a synchro, and I said that these come in pairs, and so you really have two synchros. One is connected to the telescopic sight and the other synchro is connected to the gun. The synchros produce voltage output, and it is these two voltage outputs which can be then taken, compared, and any action that is necessary taken by comparing these two, taking the difference if you wish, because it is not DC, it is AC, you may do some rectification, or all these kinds of things, or you may use an AC motor instead of a DC motor and whatnot. So this unity feedback idea of directly comparing the actual quantity with the desired quantity makes practical or physical sense in only very exceptional situations like this. In most situations, the actual quantity, of course, is actual. It's actually the motor running somewhere, or some bath having a certain temperature, or there being a certain pressure developed under a certain set of bellows or whatever. So the actual quantity is, of course, physical. It is speed, temperature, pressure, whatever. The desired quantity is in your designer's mind or on a piece of paper written as 1500 rpm. It is not a shaft running somewhere at 1500 rpm, or if the temperature is to be maintained at 27 degrees Celsius, then it is not some other device in which there is the ambient temperature of 27 degrees Celsius, so that you could compare the actual temperature with this temperature and take some action. It is almost never like that. So, of course, one is thinking of the desired quantity, the desired value, and the actual value, and the two should be equal. Strictly speaking, that's not what we mean. What we mean is that the actual speed should be equal to a number which can be specified, or which is specified beforehand. The actual speed should be 1500 rpm. There is no comparison between or made between the actual signal and a desired signal which is the same kind physically and of the same value numerically as the actual speed. So this unity feedback, and a lot of talk is made about it, because as I said, on a block diagram you can indeed show a number of signals whose values will be comparable. In fact, we have it on our example. The reference speed is 20 volts, the tacho generator output voltage is also voltage, and the two are comparable. The reference speed is 20 volts, the tacho generator voltage may be 19 volts. There is not a big difference between the two. So, in that sense, there is some comparison being made between two quantities which are of the same type and their values are close to one another. So, I could talk about a unity or a non-unity relationship between them. Of course, both the solutions that we found out are such that there cannot be equality between the two. What was the first solution? The first solution was to change the reference voltage, instead of 20 volts, increase it to 21.15 volts. Fine. So 21.15 volts is the reference voltage. The tacho generator output voltage at the desired speed is 20 volts. If you want the drive to run at the correct speed, then it should produce 20 volts. Reference voltage is 21.15 and everything is all right. But the two are not equal. 21.15 is not equal to 20. Of course, you can say that 20 is some fraction of 21.15 volt. Surely it is. But that way any number is a multiple or a fraction of some other number. There is no great significance. In the first arrangement, there was no potentiometer being used. The reference voltage was 21.15. The tachometer voltage, tacho generator voltage was directly connected into this difference device. There was no potentiometer used, there was no multiplying coefficient used at all. In the second solution, we kept the input voltage the same, 20 volts. Therefore, we required a feedback signal which was not 20 but less than that. However, the tacho was producing 20, so we put this potentiometer, or an attenuator as it is called in amplifier practice, to reduce the value from 20 to 18.85 volts. But still 18.85 is the feedback signal finally going into the comparator, 20 volts is the reference signal. The two are not equal, and they should not be equal, because if they are equal then the output is 0, the motor will not run. Think over all of this carefully. Read the relevant material from any one of the textbooks. I find that even very good textbooks have committed this mistake, or this confusion, have fallen prey to this confusion. This distinction between unity and non-unity feedback, about which a lot of fuss is made, and this idea that the system is driven by the error on the one hand, and that signal E, when the drive is running at the correct speed, is an error signal. This is where the mistake lies. When the drive is running at the correct speed, that error signal, that signal E, the output of the comparator, is not 0, but that is not the error in the system. That does not indicate that the motor is not running at the correct speed. In fact, if it is of the correct value, it indicates that the motor is running at the correct speed. So it will not be correct to call it the error detector in this case, and in fact in most cases where you have proportional control and you have a type 0 system. In such a case, that signal E should not be called the error signal if by error we understand that the actual value of the output is not equal to the desired value. Something has gone wrong somewhere. The system is in error. No, that's not the case. This signal does not represent or indicate error at all. However, it does indicate something, and it is required to produce the desired speed. Now, suppose you wanted to change the constant speed from 1500 rpm to 1000 rpm, and let's say we wanted to keep the same motor, we wanted to keep the same amplifier Ka with the same gain 200, same tacho generator. The motor is to run now at a speed of 1000 rpm. What should we do? So if you think correctly, the answer can be found out by going through the actual calculations. 1500 was produced by 1.15 volts for the value of E. Now I want 1000, so that will be reduced correspondingly. 1500 rpm was producing a tacho generator voltage of 20. Now I want 1000 rpm, so the tacho generator voltage will be less. So knowing this new tacho generator voltage and the new value of the voltage E, I can find out the new value of the reference signal ER. And all I have to do is I have to generate that value of reference signal somehow. And you can think of here a potentiometer or voltage divider arrangement, say 30 volts is applied to it, so that you can pick off some required voltage. So for 1500 rpm I pick off voltage 21.15. So there is a slider, and of course that slider is not marked in volts, it is directly marked in rpm. So when you do the set point or when you do the setting, you simply move that slider up and down till it is at against the correct mark, which corresponds to the desired speed, which will produce the correct reference voltage. And under ideal conditions, by that we mean what? By that we mean that the torque is at the rated value, the field current of the motor has not changed, the gain of the amplifier has not changed, the generator which is supplying the armature voltage, its features have not changed, etc., etc., parameters have not changed. Given all those conditions under which we made our calculations, if those conditions apply, then the speed will be at the desired value, whichever it is, whether it is 1500 or 1000 or 500. By simply adjusting the reference voltage ER appropriately, the drive will run at that desired speed. The system is of type 0. The system is not really driven by error, but the voltage input, in this case the armature or the field current, is derived in a proportional manner from the output of a difference device. The difference device does take the difference of the reference signal and the feedback signal, and that difference device is multiplied by some quantity like this gain Ka. So there is some kind of proportional idea here. Type 0 system, this kind of proportional control, but there is no steady state error. The system can operate at any specified speed without any error whatsoever. We will look into this once again when we come to the section or the material on error in control systems and system types and so forth. And so once again I will point out there the mistakes that have taken place in many of the textbooks because of this confusion. Now, the reason for using feedback was not really all this, because the operator could directly control or set the field current at the desired value so that the motor runs at the 1500 rpm speed. So why have you bothered to produce all this feedback? Now any system, any control system, whether regulator type system, whether manual or automatic, has to have a set point input if it is to be capable of running at different constant values of the output quantity. I repeat here, if you want a drive that will run at 1500 rpm and only 1500 rpm and at no other speed, then you don't need to change any settings anywhere. Once and for all they will be fixed. All you have to do is turn the motor on. There is some starting arrangement that can also be automatic. You will get 1500 RPM. In that case, perhaps you will not use a DC motor at all. You will use a synchronous motor. A 4-pole synchronous motor from a 50 hertz supply, if it is sufficiently stable supply, will give you 1500 RPM without any of all this roundabout operation. In fact, one usually has different requirements at different times. You would like the drive to run at 1500 RPM on one application, maybe at a different speed at another time. In other words, there will be this set point business or a setting business. Air conditioner, think of it once again. You don't want an air conditioner that will only produce a temperature of 27 degrees Celsius no matter what. Whether you are comfortable or not, you live with it. No, we have this set point adjustment. And so, depending on the desired quantity, the set point is appropriately selected. And this will have to be done manually. Of course, I can think of a futuristic, in fact not such a very futuristic system where you may feel that the thing is not being done manually, it is being done automatically. Imagine a air conditioner remote unit which is controlled not by pushing a knob somewhere and setting some digit somewhere, but by speaking into that remote unit. So I say 25 degrees Celsius, and that device is smart enough, it listens to what I am saying, interprets it as 25 and then does some setting somewhere. Some setting and resetting, it will have to be there is no way out. Now, is this automatic? The answer is no, because I have spoken and said set it to 25 degrees Celsius. I have given the input. The air conditioner did not automatically change it to 25 degrees Celsius. Of course, one can go to some further futuristic scenario where, say, I don't know about this temperature, Celsius, air conditioner and so on. I am too lazy to even speak out and say 25 degrees Celsius. So I have something connected to my body, say to some part of my skin, and that thing sort of senses whether I am comfortable or not. And so as things happen, I don't do a thing. That sensor there checks for my comfort in some way and says, okay, change it to 25, no, change it to 26, this guy is not comfortable, he is too cold, or no, change it to 26 from 27 because this guy is not comfortable, he is feeling too hot. Maybe you can measure the amount of sweating that is taking place. Of course, all this is futuristic nonsense. I hope we never reach that stage when we will be so lazy and we will have all these devices so that we don't have to do a thing and we are comfortable all the time. So given that fact that at the moment at least we don't have any such thing, setting, resetting, set point adjustments are there as a part of any control system, any practical control system. Therefore, for a different desired speed, change the reference voltage is not a big issue. It has to be changed. Of course, that setting can be marked already. Somebody has done all that work. Therefore, I don't adjust any voltage with a voltmeter. I simply put the slider in the appropriate mark. Somewhere it says 1500 RPM, I put the slider there. Or if it says 1200, I bring it down or up, put it against that 1200 mark. And that's what actually will happen. Nobody is going to measure any voltages and speeds and what not. So this is how typically the control works. There is some knob which is to be turned and that results in some other change. Of course, we have the on-off situation available to us all the time. That's the most preliminary or simplest kind of control that I mentioned, namely on-off control, and which is not too bad after all, but it requires a lot of attention and action. Even then you have to change it from on to off and off to on. So there has to be a change of setting. But to come back to what I was talking about, we don't really need feedback. I don't really need that tacho generator output and so on, because directly 1500 RPM requires 230 volts. 230 volts is produced by, say, 1 ampere of field current, and that 1 ampere of field current is obtained by some voltage of 20 volts somewhere. So 20 volts produces 1500 RPM. I want a different speed, different armature voltage, different field current, therefore a different voltage somewhere else. Why do I need feedback? Why do I need a tacho generator? In fact, I don't. So then why are we introducing feedback? And to repeat, and I think this point is worth repeating because one tends to forget why feedback is used. Not just because it's some fancy idea, but because we want to take care of, or we want to get over these things that are going to happen when the system is in operation. Two kinds, once again: disturbances. The load torque is not going to remain at the design value. In fact, you may want the speed to remain constant in spite of changes in the desired in the torque value, and you want the speed to remain constant without somebody making adjustment of the input voltage all the time. Certainly with a human operator it's possible to make the motor run at the desired speed even when the torque changes, and we want to make it automatic. And if you want to make it automatic, you have to see what's actually going on. That seeing what is actually going on is feedback, and then you have to make an adjustment which is based on that feedback. The speed is not correct, it is less, I have to increase it, or it is more, I have to decrease it, so I have to make some adjustment somewhere. This adjustment we want to be done automatically, and that's what the whole purpose of the feedback idea is. That is, even when there is a disturbance, we would like these adjustments to be made automatically, so that after some time delay the speed remains at the old value. Remember, there will be a transient error, there will be a short period during which the speed will deviate from the desired value, but hopefully this adjustment will be made so that the speed is back at the desired value. Even if the armature field current of the motor changes, we had assumed that it will remain constant. Even if the field current of the motor changes by a small amount, we would like the speed of the motor to remain unchanged. And many other disturbance signals one can think of. In the Leonard system, the motor is fed from a generator, the generator is run by another motor or by an IC engine. What about its speed? Its speed may not remain constant, and so on and so forth. So disturbances, disturbance variables, they are always there. One of the purposes of feedback is to see whether the effect of the disturbances can be reduced or even cancelled out completely, whether adjustments could be made. And remember, not manually. Manually things can always be done within limits, of course, automatically, so that the error is reduced or made zero if possible. Adjustments to be made so that the error is zero or as small as possible. The second is parameter values, changes in parameter values or uncertainty about parameter values. The design value is not exactly the same as the actual value perhaps, and therefore the pre-programmed control will not work necessarily. It may work in very few cases by chance, but generally things will go wrong a little bit, and so some adjustments will be required anyway. Now, if the parameters change, I don't want to keep on measuring them, making recalculations and making readjustments. I would like automatically something to take place so that the effect of the parameter variations can also be countered. The word used here in a more technical sense later on is that this change is compensated. The load torque is increased, yes, but I will compensate it. That is, I will make some other adjustment so that that load torque increase does not change the speed. Some parameter value is not the same as the design value, yes, but the deviation or the difference can be compensated by an adjustment somewhere else. Now, if we go back to our control system arrangement where we had the tachogenerator output, the reference input, the comparator device, and that signal amplified going into the motor which drives the load, with that kind of arrangement, can it handle? So, no other changes to be made. Where is the automatic adjustment in that system? The automatic adjustment is through the mechanism of that comparator device. Remember the symbol for it, circle with plus and minus, the reference signal R of t, or in our case DC voltage ER going in, the other one the tachogenerator voltage getting subtracted from it, and at the third quadrant comes out the output ET. This ET is the signal that is then driving the system, and this ET is sometimes called the actuating signal, or it can also be called the manipulating signal. That is, things are changing through this ET. Things change because this ET changes. So, one talks about it as the actuating signal or the manipulating signal. Now, the arrangement that we have, although it has feedback, we will see that it cannot take care of the two reasons for which feedback was introduced or is to be introduced, namely disturbance and change in parameter value. So, what I am saying is, now if the load torque changes, of course I am not going to measure the load torque, that is an assumption that I am making. If the load torque changes and I am not going to measure anything else other than the speed, and my arrangement is as before, the comparator ET amplified through Ka, etc., no change. So, my reference voltage of 21.15 volts produces 1500 rpm for a load torque of say 30 Newton meters, no problem there, or it could be 20 volts because the tachogenerator we have taken only a part of its voltage. If the load torque changes, then with the same reference input, and I am not going to change the reference input because the reference input corresponds to the desired speed, and I do not want to step into the thing, I want it to happen automatically. So, I am not going to make any adjustment. What will happen if the load torque changes? We had earlier worked out the design calculations under steady state conditions by saying that the armature voltage will be so much, the back EMF will be so much, etc., etc. So, take that example now and assume that the load torque changes from 30 Newton meters to 0. From 30 Newton meters it changes to 0. In other words, there is no load. There is of course still the frictional torque required for the motor to run, because we may want still the motor to run and not simply switched off. We may be changing from one job to another. So, the load torque is changed only momentarily, perhaps from 30 Newton meters to 0. Of course, one can say 30 is changed to 20, that is another calculation that you can make. So, suppose the load torque is changed from 30 Newton meters, the original value, for which the reference voltage will produce the desired speed, no error, nothing. Once the torque changes, the speed is going to change. And we went through that argument as to why the speed will change. And what was that argument? Very quickly, if the load torque changes, the total torque produced by the motor is no longer the same. Therefore, the armature current of the motor is not the same. We are assuming that the field current is kept constant. If the armature current is not the same, the armature voltage drop is not the same. The applied voltage is not being changed. If it is not being changed, then the back EMF will not be the same, and therefore the speed will not be the same. So the speed will change. But that was for the so-called open loop arrangement, in which 230 volts was being applied as input to the motor, and we had some equations which resulted in 1500 rpm under the rated conditions. But under zero load, the no load speed of the drive would be greater than 1500 rpm. But now the situation is different. We are not applying 230 volts to the armature. We are applying a voltage which is produced by this arrangement of the comparator and the gain Ka and so on. So in fact, the voltage that is produced will not be 230 volts. What will it be? Well, we need to calculate. We need to make fresh calculations to find out what will be this new voltage which will be generated at the output of the amplifier. But you can do the calculations, find out what the speed is, and you will find that it will not be 1500 rpm. And in fact, you should also see the reason why the speed cannot be 1500 rpm. If the speed were to remain the same, the tacho generator output voltage will remain the same, reference voltage is the same, the output E therefore is the same. If the output E is the same, that means the armature voltage is the same, load torque has changed, the speed cannot remain the same. So the assumption that the speed remains constant leads you to the conclusion that the speed is not the same, therefore the assumption is wrong. The speed will change. Now one can find out by how much the speed will change and compare the two situations. The very preliminary crude open loop situation, in which just applied 230 volts to the armature, did nothing about it, let the load torque vary, the motor speed will vary by a small amount, because after all the DC shunt motor is a good one for constant speed operation, and if that change of speed was tolerable, well and good. So there is nothing being manipulated, there is nothing being adjusted, there is nothing, no actuation of any kind, 230 volts fixed applied with load torque changes, the speed would change. Now we have changed the system, we are using this kind of a proportional control idea. Therefore, the reference voltage is kept constant, the reference voltage is not going to be changed, because we are not intervening manually. The reference voltage is kept the same, but because of this feedback arrangement, the speed will no longer remain the same. Of course, that is also clear, but the speed will not be at the same value as it would be if we had not used feedback. So we can compare the two situations, one of which can be called open loop, though strictly speaking it is not open loop, but what we can mean is something like this. Suppose we took this system as it were and got rid of this error detector and tacho generator and reference signal, etc., and just gave a constant input at that ET point. Say we kept ET constant at 1.15 volts, so that the armature voltage was 230 volts. So in this sense the loop has been broken. So in this sense open loop. So under open loop conditions, when the load torque changes from 30 Newton meters to 0 Newton meters, say from rated load to no load, what is the change in speed? There will be an increase in speed. What is the change in speed? And secondly, with the closed loop arrangement, that is the arrangement that we have been talking about, where feedback is used, you have the tacho generator, the reference voltage, the error detector, the amplifier Ka, and all that stuff, the additional, and that all that thing is the controller now, plus of course the IC engine and the generator which is driven by it and so on. This whole thing is now my controller. Plant is still the same old DC motor driving the grinding wheel or whatever it is. So, with this feedback controller using proportional control idea for a type 0 system, with the change of torque, what will be the change in speed? Do these calculations. I will go through them to check whether your calculations are correct. We will find that the speed change will be less with feedback than it was without feedback. With 230 volts constant armature voltage, if there is a certain change in speed with this feedback arrangement, for the same change in the load torque, the speed change will be reduced. Now one can speculate or get mystified as to how is it happening that the speed change is now less than it was earlier in the open loop case, and that too it's happening automatically. Well, of course one can get mystified, but a part of the answer is that the arrangement that we have provided, the tacho generator, the amplifier, is such that the voltage EA is no longer necessarily going to remain constant at 230 volts. We have provided for a possibility of its being manipulated or adjusted. We have provided the possibility of its adjustment. And so we should not be surprised if the adjustment is working. The only thing is, fortunately, the adjustment is working in the correct direction. The speed change is less with feedback than it is without feedback. But if the set point is not going to be adjusted, then there will be a speed change. So with type 0 system, with proportional control, with a disturbance signal of this kind, there will be a steady state error when the disturbance signal acts. However, this steady state error can be made smaller than what it would have been if we had not used feedback and if we had not used any adjustment. So feedback does provide us with the advantage or the possibility of reducing the steady state error. With the present arrangement, the proportional control arrangement, the steady state error when the disturbance signal changes or disturbance takes place, the steady state error cannot be made exactly 0, and we can see how. Because if the error were 0, the motor will run at the correct speed, ET will not change. But if ET is not changing, armature voltage is not changing, in the presence of disturbance, the speed cannot remain unchanged. So that simple argument shows that with this kind of a disturbance, that is, the disturbance is also the type 0 type, that is, the disturbance directly affects the speed. Load torque increases, speed will decrease. Load torque decreases, speed will increase. Just as armature voltage increases, speed will increase. Armature voltage decreases, speed will decrease. So the relationship between the disturbance variable, in this case the load torque, and the speed is also of the type 0 kind. Then we cannot avoid steady state error in the presence of disturbances. You can go back and use our formula that we had derived under steady state conditions and play around, substituting different values of load torque or substituting different values for the parameter, let us say KB or KT is changed, and so on. We have done this calculation again, you can do it again, and then do the same thing with feedback. That is, with the feedback arrangement, what will be the error, and see for yourself that the steady state error will be reduced. How much reduced? Well, it turns out that it depends on that gain Ka. And that too one can see why. The error, the speed not being the correct value, changes the output ET by a small amount. Now if the ET itself is of a much smaller amount because of the gain Ka being large, then the change in the speed must be of a still smaller amount. So you can work out the problem with the gain K which is Ka which is 10 times 2000, closed loop system with a gain in the forward path of 2000, and then work out the speed change when the torque changes from 30 to 0. You will find that the speed change is even less. So by increasing the gain Ka, I can reduce the steady state error, and so of course I can become ambitious but careless and say that alright, let me increase it by another factor of 10, my steady state error will be still reduced. Well, the answer is yes, but what about the transient error? We have not looked at the transient error at all. We are only looking at the steady state case. What about the transient error? We will see later that if you increase the gain too much, the transient error can be increased. In fact, with Ka not very large, the speed may simply change from one value to another, increase from 1500 to say 1510 rpm slowly but steadily. But if Ka is too large, then the speed will change from 1500 to 1510 perhaps, not steadily but in an oscillatory manner, so that during the transient period the speed may go beyond 1510 rpm, may go to even say 1600 rpm, then may go below 1500 rpm and go on oscillating like that till finally it reaches the value after sufficient number of time constants of the new value 1510 rpm. This of course is in a qualitative way referred to as some kind of instability, although the system is not unstable, but there are no oscillations. Now there are oscillations. The transient behavior is not satisfactory now. So the steady state error was reduced, but the transient behavior is not any longer satisfactory. So there are limits up to which you can go, and of course we will be looking at this in greater detail when we concentrate on the role of this parameter Ka, the gain in the forward path, how it affects steady state performance and how it affects the transient performance of the control system. This is one way of reducing the steady state error, namely increase Ka, but there are different ways. I had mentioned earlier integral control and derivative control. What we have used is proportional control. Essentially what we are doing is we have to make some adjustments when there is error, when the actual speed is different from the desired speed. How that adjustment is made, that is where we have to exercise our intelligence. The proportional idea is the simplest one, and we will redraw the block diagram to see very clearly that the kind of mistake that is there in the textbooks is not made by showing that adjustment thing separately. So it will become clear that in that sense the adjustment is proportional to the error, but not E proportional to the error or the difference between the actual speed and the desired speed. But by changing the mechanism of this adjustment, by introducing the possibility of some kind of integration over a period of time, we will see that the steady state error can be made 0, although the transient error will not be 0, and once again the transient error may have some unwanted features. So for a type 0 control system with proportional control with disturbance, we may have non-zero steady state error, but with integral control we may be able to reduce or make the steady state error 0, but we will have to look at the transient performance.